All right, just going to give everyone just a few minutes to get in here. It's Friday, it's noon. All right, let's get this show on the road. It's Friday and it's noon. That means it's time for Tech Art Talk Live. Hi, I'm Chris, and I will be your host for today's session. And today we're going to be going over one of the topics that everyone says that they are really knowledgeable about, but very few people really understand the rules of, and that is what PBR is. PBR, or physically based rendering, is kind of like the newfangled lighting model in all rendering, real-time rendering engines. A lot of people like physically based rendering. A lot of people don't like physically based rendering, but you're going to find it just about anywhere. And from my humble opinion, it is just about the best and the fastest way to get realistic looking images. Now, it's not necessarily the greatest for stylistic rendering, but if you're going to get anything close to realistic and you want kind of very dependable, behavior driven kind of materials, well, then PBR is the way to go. So, with without ado, let's get this started about going on about my PBR crash course. Okay, this is my PBR crash course, and a lot of you are saying, is this going to involve math? Uh, Today, I'm going to show you some math, but we're not going to go into the math, and I'm not going to hold you accountable for the math. Next week, I just might hold you accountable for the math, but that is something we'll discuss about later. All right. Now, a lot of you, like, if you're like born like before 1985 or something, probably got used to doing computer graphics using the old illumination model, which is called traditional Phong lighting. Um, what was it? Those guys over in Utah, believe it or not, guys like Jim Blinn and uh, what's his face from Pixar. They all got together and they invented computer graphics really back in Utah back in the 60s and the 70s. And Fong was one of those guys that was getting his PhD at the time, and he decided, hey, let's try to create a duplicate or a kind of a simulation of how light lights objects. And they came and Wei Fong came up with this model, and it takes advantage of the surface normal, which is this green arrow, a light ray coming in, which is this yellow model, and a viewpoint, which is this white arrow coming off, pointing at the V. So if you have all three of those, then you can pretty much go ahead and illuminate any kind of sort of light on any sort of object. And what he did was he came up with this function called this. Now, don't freak out about that because all of this gobbledygook is stuff that you manipulate on an everyday basis when you're ever doing any kind of computer graphics. But this is the actual formula that he came up with. But what this corresponds to is this red stuff here. This is your ambient lighting, or this is the lighting that is in your environment that's on by default, or the color of your shadows. This stuff in green is your diffuse lighting. This is basically your normal albedo, your base color lighting. And then the specular lighting is the lighting, it is the real bright spot of where the of where the angle hits the object just so right that if you aim the camera and the light angle at this right, you get a little hot spot on there. Well, that hot spot is called the specular component. But that's all the math we're going to go into now. We're going to all talk about going into what the basics are. So the ambient light is the basic color of what your object looks like inside of the dark. This is the basic minimum darkness that your object is going to be at. And so there is no light. And there is there is an illumination that you might see in like World of War in Minecraft or something called no light, but we're not going to be talking about that. But we're going to go right to the ambient light model. And so the diffuse is your standard albedo, your base color shading model. And this is kind of based between the the position of the object and the relevance to where it's facing towards this light object. So objects that are facing towards the light are going to be brighter than objects that are facing away from the light. And now the specular, once again, that is the hot spot. Now that's not only dependent on the position of your object, but also the position of your light and the position of the camera. And that's why the specular point kind of floats around depending on where you look at it. And these are all various other deviations of the illumination model beyond the Phong basics. But basically, when you get the ambient and you add it to the diffuse and then you add it to the specular, you get the basic illumination or the Phong illumination. Now, that was like in the 60s and 70s. Well, around in the 90s, folks started coming up with what if we actually were to duplicate the real behavior of how light actually does interact with real objects and so forth. And then they came up with the physically based models, physically based shaders. And really, what they are is duplicating the behavior of real light bouncing off of real materials. And this is something that has been optimized and can be found in real-time engines. But there's just really just one shader to rule them all. And we're going to get to the reason why. But usually you see a lot of node-based shading languages like in UD4 and so forth that kind of like make this a little bit easier to work with artists. Now, the TAs are still on the hook, but really these physically based shaders, they're kind of tough. They're very difficult, and they're very difficult, and they're very fragile. And so that's why there's only one shader to rule them all. And that's because there's one shader. It kind of encapsulates all the functionality the physically based shading can do, and it combines it into one node. And that's right. I don't want you going into that. And so that's why they hook it up to make it really easy to work with. And let's see. Okay, so this is actually what physically based rendering looks like. No, please don't freak out when you see this. Yep, that's it, folks. Okay, now this equation is really ugly looking. And in fact, but it's really, really important because this is also the same rendering equation that is used when creating ray tracing. And so therefore, next week, we're going to be going on just understanding what this rendering equation is because it has a lot of pieces. It's got a lot of stuff going on here. And you know what? I'm not even going into that. But one thing you do need to know about physically based rendering is that it's very challenging to actually implement. And it's very fragile, but it is very doable. In fact, what is physically based rendering? It's really just a collection of strategies to approximate the best rendering equations and get them done as quickly as possible. So therefore, it's been done. There's a lot of refinements, there's a lot of optimizations, and there's a lot of shortcuts going on here. And so the overall shaders are very fragile, so therefore that's why they encapsulate them into one node because they want you to keep your hands off. They don't want you monkeying around in there. You got it? Yeah, keep your mitts off. Okay, but the cool part is that when you do it this way, you can leverage the texture maps. And so the power of PBR really lies in the usage of its texture map. And so all the components of the basic PBR behavior can be driven by specific texture maps. And that's really cool. So that despite the contents of the texture map, the material is going to do its best to accommodate. So you can throw whatever you want inside of the PBR shader, and the shader is going to do its best. So therefore, you could get really complicated shaders. Okay, now I got to warn you that hey, you say, hey, we're using PBR, we're using physically based rendering. We can end up with we can end up with great looking materials. No, that's not the case. And there are some issues that you need to be aware of when using PBR, and that's really what we're going to be discussing out for the rest of this lecture, is because even though you can put textures on every n values, on every one of the components in PBR, you're going to end up with a really sloppy looking material. Yep, yep, yep. It can look like hell. And a lot of times you're going to end up with materials that don't make sense. And even nuttier are materials that don't really exist in this world because we're trying to duplicate the way that real light behaves against real surface objects. Well, those materials that the way they're reacting just doesn't happen in this world anymore. And so if you're not careful with, okay, yeah, here's the thing about the texture maps. I wanted to put a note in here. The registration, that means make sure that the textures are all lined up with each other appropriately so that when you actually do it, the corresponding elements in the PBR components, they overlap each other because otherwise the material is going to be out of alignment. It's going to look real nutty and so forth. All right, so as a quick example, I wanted to just toss in here real quick what this Uber node looks like. Now I'm going to show it from UE4. We've got a test scene here, and I'm going to go right in here. Now here is this PBR shader. This is the PBR shader, the one to rule them all. You see it's got slots in here, and you can plug textures, you can plug values, whatever you want in here. But we're probably going to be focusing just on the base color, the metallic, the specular, the roughness, the normal color, and then the ambient occlusion. Of course, we can do all these other more advanced features, and we're gonna maybe not talk about emissive right now, but needless to say, these are all that is, but this is all kind of like what are the parameters that are exposed to the physically based rendering environment inside of UE4. And if I'm not mistaken, then Unity has a very similar situation, and I would not be surprised if Lumberyard has a very similar setup as well. All right, let me return back to my lecture. Okay, so what are you going to do? Okay, if PBR is really complicated and really hard to work with, and it's very fragile, well, what's the best strategy to deal with? Well, know the basic PBR rules and make sure to have lots of reference for the materials you're creating. Nothing beats having to adjust the material of your model, of your material, and then having a reference of some actual fabric and some actual plastic and some actual metal. And you can see it in hand. If you can't see it in hand, well, then get lots of photographs for it. There's lots of tools out there that are good for that. And okay, it says master layers and masks in Photoshops, and yeah, and what you could do is take advantage of once again, this has to do with registering and making sure that all your objects work in course with each other because you're going to need masks and multiple layers in there. And but there are, before, I mean, Photoshop used to be the way that you had to paint PBR textures, but now there are other packages about that, like Substance. Substance is a really good package that allows you. Though there are others, but Substance is kind of like very well known. So the overall rule is that know your materials, history, and its backstory. So the nice thing about Substance and the nice thing about working with PBR is that you can paint and you can put into the texture, you can put in the history of the object, you can put wear, you can put tear, you can put rust, you can get all that stuff and then mix it in all at the same time. And you can have metals interacting with layers of plastic and paint and flesh, and you can have them all within the same texture map, which is like really, really cool, but you got to kind of know what you're doing. And so I'm going to start going over what are the basic PBR rules. Well, the first rule, and probably the most important rule of all PBR basics, is the material metal or not? This kind of manipulates the whole behavior of this. So you might want to hear this. People might say, is the material metal? Or they might call it electric. Is it an electric or a dielectric? A dielectric is a material that is not metal. It is like something other than metal. And so I'm going to be a Nazi about this. You can either be a yes or a no on this answer. There's nowhere in between because I have yet to see any kind of object that exists in our world that's sort of metal and it's sort of not metal. Either a material is either metal or it's not. And so that means it's either a 1 if it's metal or a 0 if it's not. Okay, now a texture map might have complex combinations of electrics and dielectrics. That means you can have stuff that's metal and non-metal, and therefore your metallic map actually acts like a mask to show what is metal and what is not metal. And uh-huh. And now we mentioned this a couple weeks ago about linear color space because the metal map is really just a mask and it's really ones or zeros. It should be in linear color space. If it's not, then you get very possible end up with some very nutty looking results here. So once again, know your material. If you have an object that's metal, but it's painted, is the paint that you're looking at, is the paint itself metal? No, it's actually some kind of plastic or some kind of polymer. If you have areas that are scratched or peeled off and the paint comes away, that area underneath definitely is metal. So that's why you really got to understand to know your materials. Now here's an example of a good metal map, and you can see it's pretty much just like a mask. Everywhere where you see it is white within the edges of the little pattern there, that is where that is metal. Everywhere it's black is not, and that is corresponding to where probably it's paint or rust or some other kind of grime or oil or something. And here is a metal map supplied by Nick Zuccarello, who was very gracious in supplying the model that we're going to be showing interactively. So what I'm going to do is I'm going to jump into my UE4, and I happen to have the metal map here. The metal map here, it's what we have here is a map that is a combination. For the red channel is the AO, the green channel is roughness, and the blue channel is metal. So I'm going to go ahead and grab the blue channel here, and I'm going to put this right into the metallic, because that will tell me if it's metal or not. Now we still can't see anything yet, but really of all things that are considered, your metal map is probably your most important metal. So that's why that's the first most important thing, the first most important texture to deal with. And that's why I always like to include it first. Okay, the second thing you need to worry about is how shiny is the object? What is the shininess? And more importantly, what is its roughness? And usually it's either listed as is the thing shiny or is it roughness? And it depends. I think in UE4, it's roughness. And so if it's shiny, then the shiny values have a 1. If it says roughness, and then the roughness has a value 1. And they can go either way, and it depends on your real-time rendering engine. Okay, all objects have some kind of reflection. And so that's why there is shininess or roughness is how much does that plastic objects reflect. Even even objects almost as much as chalk. Chalk is about as rough as you can guess, but it still reflects light somehow. And so that reflection is called the Fresnel effect. And let me go into give a quick introduction of the Fresnel effect. Okay, here we have is a rubber ball. Yes, it's rubber. You know, kind of imagine this was like black leather, black latex on somebody at the kinky nightclub here. But anyway, here we have is this black rubber here. And you'll notice that in the center, when we're looking at the black rubber, it looks dark. And that's because, according to the Fresnel effect, the amount of reflection happening right where the center of the object is, or the normal is facing right at the camera, is minimized. However, as you go down the sphere and the normal turns away and becomes perpendicular to the camera, the more shininess it gets. And so therefore, the Fresnel effect is like it's right in the center. You're not going to see much shininess. But as you go on to the edges of the object, as they kind of curve away from the camera, you're going to start to see some of the shininess. And that's what this overall graph is that all objects do reflect some kind of amount and so forth. And it might be very small, like rubber, or it might be very large like chrome. And those are your base reflectivities. But as you'll notice that as you go away from the center and more towards the edge, or where that surface normal is turning away from the camera, it starts to become more and more reflective, and it starts to reflect even more. And so that's why you got to know what the how shiny or how rough your object is. All right. And so this is also a yes or no answer, but it could also be yes, sort of. And so you got a lot of depending on your material. And so you get the full range between going between 0 and 1. And because we're going between 0 and 1, we're going to get the full representation of linear color space. We don't need this to be compressed. We don't want anything funky going on, but we want to well, we don't. We want to just kind of keep dealing with this, and we want to go in and just deal with the linear color space. Think with that. Oh yeah, by the way, UE4 does use roughness according to the slide, so it's called. It covers the amount of reflection. So a roughness map look like this. So if this is going into UE4, then the roughness is white, and so therefore the shininess is going to be black. It's a little bit inverted the way that it sounds here, but because UE4 is going towards roughness, roughness is a value of 1. So in here, the roughest areas uh, are going to be the areas in white here, and the areas that are darkest are going to be the shiniest. Now in Nick's Canon here, we have some areas that these are corresponding to the Canon, like this is the Canon. This is the Canon metal itself, and then we see a lot of um, roughness here according to the sides, and then we've got wood, and the wood is going to be very rough. But the metal itself is a little bit more smooth, and so the wood surfaces are going to be the brightest, and the metal surfaces are going to be a little smoother and so forth. So let's go ahead and hook that up to my shader, and we'll start to see this thing coming along here. And so the metal map here is in the green channel, and we're going to hook this right up to the roughness channel. Now we still can't see anything in here, and here's our thing, but we can kind of get the feeling that it is moving around a little bit. Let me see if I can expand this just a wee bit more. Okay, there's our metal. Okay, so we are seeing some kind of reflection in the way that the light reflects it. We are seeing some light reflected off of some of the objects. All right, excellent. Okay, now, rule number 3, specular. Now, I don't really know if this should be a rule, if this is just kind of slipped in here just because we need to include it. But all metals have a base color of black. All metals are black. They don't have any kind of color at all. That's the kind of weird thing, but that's what makes PBR show. Yes, all metals are black. However, most metals are very shiny. And so therefore, what we're looking at when we see a metal is not the base color of the metal. What we're looking at is the reflection on the metal. See? And so therefore, non-metallic objects really don't have specular color because the metals are kind of dependent. The specular color kind of makes up what the color of the object. So the specular color really isn't used very often because unless the object is metal, you can't really see specular color. Okay, and in fact, in most PBR renderers, including UE4, the default specular color of a non-metal defaults to white. That's what they give you. And they kind of hide this back for you, but keep this in the back of your head because knowing that unless you are manipulating, unless you are dealing with a metal material, you can't actually manipulate the specular color. Okay, so in other words, just keep it simple. Multiply a color against a roughness or metal, and exactly. So let's take a look at the specular. Actually, Nick's thing doesn't have a specular color because all the specular color bouncing off of his Canon is white, and so we do not have a specular map for that. But okay, now we finally get to rule number 4. Okay, the base color, the albedo. Now, this is the place where artists are most friendly with. This is where they like it because they have the most area of freedom. This is the kind of map that gives them the freest amount of control because there really are no rules. Non-metals can be any color, but regretfully, metals are black. And so therefore, metals are black, so therefore, you're going to have to color your metals with the specular color. And this is the registration for. And everything up until this point, well, except for I'm sorry, the specular color, that's not done in linear color. But for base color and albedo color, make sure that you're using sRGB color. That means it's in gamma space. And the reason why we want it in gamma space is because we want to see that actual color compression. If we don't see that color compression, then then there's going to be confusion. UE4 and every single rendering engine alive is assuming that if you have any kind of like color for base color, it's coming in as an sRGB color, and it's going to be doing all the conversion to linear before it processes that color, and then it's going to convert it from linear after it's done processing. Then it's going to convert it back to gamma color, and it's going to give it to you the way you expect it to see it. And all renderers assume that this is what's going to happen. So that's why you got to make sure to put in sRGB color and don't put in linear color for your base color or your albedo. Okay, here's an example of that same kind of grid pattern that we are looking at here. It looks like this is maybe some kind of yellow paint or something on here, and this is almost the kind of flip side of the metal side. Wherever you see yellow, that is where it is not metal. And everywhere where you see white or dark gray here, that's going to be where you see the metal side of this. And so let's take a look at the NICS map on here. And what we can see here is we've got the yellow here, and the kind of gray or the dark stuff. This is where all the metal is. But all of the other colored stuff, this is going to be where all the non-metal stuff is. And let's go ahead and hook that up to the material, hook that up to the shader. So we're going to hook up my base color. We're going to hook it up to the base color here, and we should start to get something that's starting to look pretty darn good. All right, now you can see the play of where there is metal elements mixing with non-metal elements, like in the cannon itself, and then where you see the strict non-metal stuff, like in the wood of the wheels, you're going to start to see something that's very rough and very standard and so forth, while the area inside of the cannon can be very smooth. Now, these are all just from the texture maps, so really good example here. Okay, now this is something that's not really a rule because it's really more of essential. Part of getting the PBR to look really good is your normal map. Now, normal maps are almost an entire science unto themselves, but really what normal maps are really good at is taking the normal, the surface normal. Remember how we said that the surface normal was very dependent on its angle and its relationship to the camera on how it actually rendered its color and how it reflected all the shininess? Well, normal maps basically go and manipulate all those little surface normals, and they make those normals behave like they're doing something that they're not supposed to. And they're essential for any kind of material to look good because no material is absolutely flat. Every material has some kind of like microscopic undulations on there that get in there. And so a lot of folks use ZBrush, and which is a package that will allow them to sculpt high-res detail and really get that kind of porous and kind of like pitted behavior inside the material. Well, that pitted material is probably too fine resolution to actually be reflected into the mesh, but it makes for perfect elements to go inside of the normal map and so forth. And so here's an example of a normal map that, as you can see, it's some creepy looking iconography. And here is the normal map for the grid pattern that we're looking at. Now you're probably going, why are they always blue? Well, they're always blue because really the normal map is not really a color, it's really a vector showing the direction of where the normal is pointing. And most of the time, the normals are pointing at us. And since we're looking down the z-axis, which is the blue axis, that's why we see mostly blue when we're looking at normal maps. Just kind of an interesting tidbit there. Okay, here is Nick's normal map for the Canon. And we see we got a lot of curvature like in the wheels, and we got a lot of nice curvature here in the uh, in the Canon body itself, but things are relatively flat, but it has some interesting surface detail in here for the wood grain. Let's go ahead and hook this up here. And so here's the normal map. I'm going to hook that up onto here. And now it's going to start to really take light because you're going to start to see reflections, and you're going to start to see a lot more detail kind of coming into that with those new changing normals. Really, really good looking stuff here. All right, now I said that we weren't going to talk about it, but I guess I lied because now we got to talk about emissive. Now, I don't have an example for emissive, but here's the rule about emissive. Emissive makes your material look like it's glowing. It can start at 0 and go to 1, but usually anything greater than 1 causes the visual effect to happen inside of the engine, and it creates this by intent. It's not a mistake, and it goes beyond 1. And anything beyond 1 makes your material start to look like it's glowing. Actually, what's going on here is a visual effects process of where the surface is rendered white, and then it goes through a post process where it's blurred and then comps back on top of it. But that creates the emissive effect greater than 1. But the most important thing to understand is that emissive objects are not light sources. They look like they're really bright, and they blur like anything, and they look like they know what they're doing. But in reality, emissive objects are not light sources. You cannot use emissive in order to light a scene. Okay, so I'm not going to put any emissive onto the Canon because the Canon really doesn't have any kind of emissive elements. But as icing on the cake, what we discovered, the the 4 or 5 texture maps that we talked about earlier, the 4 or 5 components of the material that we talked earlier are the essential ones. Now we're going to talk about some of the extra ones. Now the ambient occlusion is a texture, or it's an image that shows where light has a real difficult time getting into. These are the deep nooks and crannies in the recesses in the surface where light has a really hard time getting into. And so therefore, instead of just leaving that up to the ambient, it goes ahead and makes the material looking darker. And it also makes the material look a little bit crisper, and this kind of adds to the realism. And because the ambient occlusion is kind of a 0 to 1 kind of thing, it goes to full light to dark and so forth, it does not really deal with color, then it's best created in linear color. And you're most probably, if you create an ambient occlusion texture map, it's going to be created inside of linear color. Now, the other map that you might deal with is a height map. Now, a height map is kind of like the cousin of a normal map, and you use a height map in order to actually push the vertices of the object towards a specific direction, well, mostly along the area of the normal and so forth. But the implication of that is that your geometry needs to have a little bit more detail, a little bit more vertices in order to hold that height information. And in most situations, don't use height maps, use normal maps. However, when the silhouette of your object needs to be seen and you need to see the deviations and the perturbations created by the height map in the silhouette, then go ahead and use the height map. And you might be able to actually use some tessellation in order to get that. And height maps are also in linear color. And so here are some examples of a height map, which is on the right, and an ambient occlusion is on the left. Notice here that it's kind of dark around the edges of the little kind of like little bumps here, and that's because light in general has a real tough time getting in there. And here is the AO map that Nick supplied. And I'm going to go ahead and hook up my AO to my, right up here to the ambient occlusion. And this definitely helps things look a little crisper here. I'm going to go ahead and save this and compile it and just kind of like take a look at this inside of the scene here. Okay, so this is what the cannon actually looks like, and I'm going to walk around and look at and so overall, what we are looking at is a very realistic material, and it really does a good job of avoiding that kind of a plasticky behavior, and it really kind of makes things look more realistic. All right, well, I hope you enjoyed the coverage that I gave today of PBR. It really wasn't too bad mathematically, and really there's just some kind of rules to deal with when dealing with that because there's a lot of things that you kind of need in order to make sure it works properly. So next week, what I'm going to cover is that rendering equation. I'm going to go and explain what are all the components of that. And it's real important to understand that rendering equation because in a couple weeks, we're going to be talking about ray tracing. Ray tracing, everyone's heard about it, but very few people actually understand it real well, and we're going to give a quick crash course into ray tracing as well. Okay, if you like what you saw today, go ahead and subscribe to my YouTube channel. Check me out, Chris Rhoda, on Facebook, and check me out on LinkedIn, or TechArtEDU on LinkedIn as well, or on the Facebook page, or go to the TechArtEDU website, because there is a website now for TechArtEDU. Register for me. Drop your name by. I'll make sure that you get all of the changes and updates to whatever TechArtEDU is doing. All right. Thank you very much for joining me today, and I look very much forward to seeing you all again next week. Until then, have a great week. Bye.